Look at our planet from the cold void of space, and the defining feature is undeniable. A brilliant blue sphere suspended against the darkness. With oceans covering over 70% of its surface, water feels like the most natural and abundant substance in our world. But from the rigorous perspective of astrophysics, this vast global ocean is a glaring, almost impossible anomaly. 4.5 billion years ago, Earth did not begin as a blue paradise. It was born from a violent, swirling accretion disk of dust and stellar debris. In its infancy, our planet was an incandescent, churning sphere of molten magma, subjected to relentless bombardments and orbiting dangerously close to a young, extremely volatile sun. At this specific proximity to the star, the immense thermal radiation and fierce solar winds should have completely vaporized and stripped away any lightweight, volatile compounds. Water, in particular, should not have survived the fiery birth of our planet. By all established laws of thermodynamics and standard planetary formation models, the inner solar system acts as a cosmic furnace. Earth should realistically be a barren, desiccated rock, entirely devoid of moisture, much like Mercury or the desolate surface of our moon. Yet, the water is here. It fills deep ocean basins, carves continental landscapes, and permeates the very mantle deep beneath our feet. The precise substance that underpins every biological process drives our complex climate systems and ultimately dictates the longevity of our technological civilization is thriving in a region of space where it mathematically should not exist. This deep physical contradiction fractures our simplest models of rocky planet evolution. It clearly implies that to understand the wettest planet we know, we must look far beyond our immediate cosmic neighborhood and question the very architecture of the early solar system. Today, we are going to explore, where did Earth's water come from? Before we journey back to the chaotic dawn of planetary formation, please take a moment to like this video, subscribe to the channel, and leave a comment below letting us know exactly where and what time you are watching this documentary. To resolve the paradox of our oceans, we have to rewind the clock roughly 4.6 billion years. Before there were planets, before there was a recognizable sun, our solar neighborhood was merely a cold, formless cloud of interstellar gas and dust. As gravity triggered the collapse of this molecular cloud, the strict conservation of angular momentum forced the infalling material to flatten into a massive, spinning structure known as a protoplanetary disk. At the dead center of this maelstrom, the crushing weight of hydrogen and helium ignited a protostar. This infant sun, operating in its violent T-Tauri phase, was not just emitting light. It was radiating fierce thermal energy and blasting the surrounding disk with powerful stellar winds. Because of this concentrated central heat source, a permanent and unforgiving temperature gradient was established across the entire solar nebula. The inner regions, positioned directly in the blast zone of the young star, were subjected to intense frictional heating and radiation, pushing ambient temperatures well over 1,000 degrees. Meanwhile, out in the distant fringes, the disk remained plunged in the deep freeze of the interstellar void. This thermal architecture is the fundamental blueprint that dictated the chemical makeup of every planetary body we know. In the near vacuum of the early solar system, temperature alone determines whether a specific compound exists as a swirling gas or solidifies into a microscopic grain. In the scorching inner disk, only materials with extremely high melting points could condense into solid matter. These are known as refractories. Heavy metals like iron and nickel, along with resilient silicate rocks, were the only substances capable of surviving the heat without vaporizing. Consequently, the building blocks available near the sun were strictly metallic and rocky dust grains. Lighter, more volatile compounds, including water molecules, carbon dioxide, methane, and ammonia, could not condense under these conditions. The relentless stellar heat kept them strictly in a gaseous state, preventing them from clumping together to form planetary foundations. Because the fierce solar wind was constantly pushing lighter gases outward, The inner solar system was effectively swept clean of the very ingredients required for an ocean. As you travel outward through the protoplanetary disk, the radiant heat of the sun diminishes according to the inverse square law. Eventually, you reach a critical, invisible boundary. Astrophysicists call this the snow line or the frost line. This is the precise radial distance from the star where the ambient temperature drops below roughly 150 kelvins. Below this thermal threshold, the laws of phase transition in a vacuum shift dramatically. Water vapor no longer remains a volatile gas. It sublimates directly into solid ice crystals. In the structural map of our early solar system, this freezing boundary stabilized at roughly 2.7 astronomical units from the Sun. This places it squarely in the middle of what is now the main asteroid belt, sitting directly between the modern orbits of Mars and Jupiter. Crossing the snow line changes the rules of planetary construction entirely. In the outer solar system, water ice did not just exist in passing, it acted as a primary building material. In the cold dark of space, ice behaves physically like rock. Because oxygen and hydrogen were vastly more abundant in the primordial nebula than heavy metals and silicates, the total amount of solid material available beyond the snow line was exponentially greater than in the inner system. This sudden, massive abundance of solid mass allowed nascent planetary embryos to grow at an astonishing rate. They rapidly became massive enough to exert tremendous gravitational pull, eventually sweeping up the surrounding hydrogen and helium gas to become the massive gas giants and ice giants we see today. The thermal physics of the snow line is the exact reason Jupiter is a behemoth of gas and ice, while Earth is a highly compressed, compact sphere of metal and rock. But the implications go far deeper, exposing a profound astrophysical contradiction. The snow line creates a severe geographic separation between the raw ingredients for life and the specific environment required to sustain it. For a rocky planet to maintain liquid water on its surface, it must orbit relatively close to its host star, resting in a delicate thermal region known as the habitable zone. However, as the mechanics of the protoplanetary disk dictate, the solid materials required to physically build a planet in that habitable zone are entirely devoid of water. The regions where liquid oceans can survive are the exact same regions where water could not physically condense during the planet-building phase. By the strict laws of early stellar dynamics, a rocky planet situated in the habitable zone is born completely dry. And right here, this physical mechanism begins to connect with a much larger question regarding the longevity and frequency of biological life in the universe. If the natural architecture of a planetary disk strictly isolates water in the outer, freezing dark while leaving the warm, rocky worlds completely barren, then the emergence of a global ocean is not a default feature of planetary formation. It requires a secondary mechanism, an active dynamic delivery system, to bridge the immense gap between the frozen reservoirs of the outer system and the dry planetary embryos of the inner system. In the context of astrobiology and the search for extraterrestrial intelligence, this disconnect represents a terrifying cosmic bottleneck. If a young star system fails to develop the precise gravitational mechanics needed to transport water inward after the planets have formed, its rocky worlds will remain permanently sterile. The chemical segregation created by the snow line could very well act as a great filter, a silent universal mechanism that drastically limits the number of life-bearing worlds scattered across our galaxy. To ensure this is not merely a theoretical construct tailored to explain our own solar system, modern astronomers have turned their attention into the deep sky, using advanced radio telescope arrays to peer into distant star-forming regions. We are now actively observing the chaotic birth of alien planetary systems. Through the detection of millimeter wavelength emissions, scientists have successfully mapped the thermal structures of active protoplanetary disks light years away from Earth. We are observing these exact snow lines in real time. we can map distinct rings and dark gaps where carbon-based molecules and water vapor are actively transitioning from gas to solid ice, confirming that this chemical segregation is a universal cosmic process. The absolute laws of thermodynamics hold true across the galaxy. Every rocky exoplanet currently coalescing around a young star is facing the exact same deficit of moisture that early Earth experienced. At a planetary scale, the meaning of this structure alters our entire understanding of our own existence. Earth was constructed in the wrong neighborhood to possess an ocean. The primary materials that formed our deep mantle and our rotating iron core were fundamentally dry, baked relentlessly by a furious young sun. The vast reserves of frozen water were safely locked away hundreds of millions of miles out into the void, lingering beyond the snow line within icy comets and distant planetesimals. For our primordial planet to somehow transform into the blue, life-sustaining world we recognize today, the static architecture of the early solar system could not remain peaceful. It had to be violently disrupted. The water had to move. If the physical architecture of the early solar system demanded that Earth was born completely dry and the water had to be delivered from the freezing outer regions, we are faced with a monumental forensic challenge. How do you trace the origin of a liquid that constantly flows, evaporates, and changes states over billions of years? To solve the mystery of our oceans, scientists cannot merely observe the behavior of water molecules on a macroscopic scale. They must look deep inside the subatomic structure of the water itself to find a cosmic fingerprint. The key to this investigation lies in the fundamental nature of isotopes. The vast majority of hydrogen in the universe is the simplest element possible, consisting of exactly one proton and one electron. But during the extreme energetic chaos in the immediate aftermath of the Big Bang, a tiny fraction of hydrogen atoms fused with an extra neutron. This heavier, stable isotope of hydrogen is known as deuterium. When an oxygen atom bonds with normal hydrogen, it creates standard water. But when it bonds with one of these heavier isotopes, it forms semi-heavy water. In the modern laboratory, this distinction might seem like a minor chemical curiosity, but out in the violent, swirling expanse of a protoplanetary disk, the slight mass difference between a normal hydrogen atom and a heavy deuterium atom changes everything. The early solar nebula functioned as an unfathomably large isotopic sorting machine, driven entirely by quantum mechanics and extreme thermodynamics. At temperatures near absolute zero, far out in the dark reaches of the outer solar system, chemical reactions behave differently. Because deuterium is twice as heavy as normal hydrogen, it has a lower zero-point vibrational energy. In simple terms, chemical bonds involving heavy hydrogen are slightly stronger and require more energy to break than bonds with standard hydrogen. In the deep freeze beyond the snow line, where energy is incredibly scarce, the formation of water ice heavily favors the inclusion of deuterium. The colder the environment, the more heavy hydrogen gets locked into the ice crystals. Conversely, closer to the young sun, where ambient heat provides plenty of energy to break chemical bonds, this isotopic favoritism disappears, and water vapor maintains a lighter profile. Therefore, the precise ratio of heavy deuterium to standard hydrogen functions as an immutable cosmic thermometer. It permanently records the ambient temperature, and by extension the exact physical location of the region of space where a specific batch of water ice originally coalesced. To utilize this mechanism, planetary scientists first had to establish a definitive baseline for our own world. Through decades of rigorous sampling from deep ocean trenches, polar ice caps, and atmospheric vapor, geochemists established a standard metric known as standard mean ocean water. Across the entire hydrological system of our planet, the isotopic signature is remarkably consistent. For roughly every 6,400 standard hydrogen atoms, there is exactly one atom of deuterium. This specific fractional value is the fundamental chemical fingerprint of the Earth. But the problem does not stop at simply measuring the signature. What makes this isotopic ratio the ultimate investigative tool is its incredible nuclear resilience. Water on our planet is relentlessly dynamic. A single microscopic droplet might be boiled in a deep-sea hydrothermal vent, trapped in a glacier during an ice age, consumed by ancient biological organisms, and blasted into the stratosphere by a volcanic eruption. Yet, through billions of years of relentless phase changes, biological cycling, and tectonic recycling, the fundamental nuclear ratio of the isotopes within that water remains stubbornly intact. The signature cannot be erased by standard planetary geology. This leads to a profound consequence for astrophysics. We are no longer forced to guess where our oceans came from based on orbital proximity or planetary size. We have the capability to conduct a definitive cosmic paternity test. By analyzing the light spectra of distant celestial bodies, or by using mass spectrometry on meteorites that fall to Earth, we can read the internal isotopic ratios of the water locked inside them. If the water inside a distant celestial body perfectly matches the ratio of 1 to 6,400, we have found a potential donor. If the ratio diverges sharply, that entire class of celestial objects is definitively ruled out. However, this tracking model is not without its extreme scientific limits and modern debates. The method assumes that the baseline we measure today accurately represents the oceans of the primordial Earth. But planets are not perfectly sealed systems. Over billions of years, the intense ultraviolet radiation from the sun constantly bombards the upper atmosphere, breaking apart water vapor molecules. The lighter, standard hydrogen atoms are more easily accelerated to escape velocity and lost to the vacuum of space, while the heavier deuterium atoms are left behind. This process, known as hydrodynamic escape, means early Earth was slowly bleeding light hydrogen into the void, suggesting that our primordial oceans might have had a slightly lower isotopic ratio than they do today. Correcting for this atmospheric leakage requires complex mathematical models, and it remains a point of intense friction among planetary atmospheric scientists. At a planetary scale, the meaning of this technique changes completely, extending far beyond the history of our own blue world. The exact same isotopic mapping is currently being applied to the search for habitable exoplanets across the galaxy. Next-generation orbital observatories, like the James Webb Space Telescope, are designed to read the isotopic signatures in the atmospheres of alien worlds passing in front of their host stars. Understanding the exact mechanisms of isotopic fractionation in our own solar system is the absolute prerequisite for identifying true ocean worlds light years away. If we can master the isotopic fingerprint here, we unlock the ability to scan the cosmos for environments capable of sustaining biological life. And exactly here, this rigorous method of isotopic fingerprinting begins to connect with a much larger historical question. Armed with the precise chemical signature of Earth's oceans, 20th century astronomers turned their instruments toward the sky. They looked past the dry, rocky planets, aiming their sensors at the most spectacular, ice-rich nomads of the deep solar system, absolutely confident that they were about to identify the grand architects of our oceans. For decades, the most elegant and widely accepted solution to the origin of Earth's oceans was written right across the face of the moon. When you look at the lunar surface through a telescope, you are not just seeing impact craters, you are looking at a fossilized record of a chaotic and violent epoch known as the Late Heavy Bombardment. Roughly 4 billion years ago, long after the primary planets had formed and begun to cool, the inner solar system was suddenly subjected to a catastrophic influx of debris. Gravitational instability in the outer solar system, likely driven by the shifting orbits of Jupiter and Saturn, violently scattered millions of objects from their stable orbits, sending them hurtling toward the sun. Earth, with its massive gravitational well, caught a tremendous amount of this crossfire. In the context of the water paradox, this violent era seemed to provide the perfect delivery mechanism. If the infant Earth was baked dry by its proximity to the sun, the late heavy bombardment offered a way to import water after the planetary surface had cooled enough to retain it. And the most obvious candidates for this cosmic delivery service were comets. Originating from the freezing, desolate realms of the Kuiper Belt and the distant Oort cloud, comets are essentially dirty snowballs. They are massive amalgamations of primordial dust, rock, and millions of tons of frozen volatiles, primarily water ice. The hypothesis was incredibly straightforward and intuitively satisfying. Earth formed dry, the solar system went through a period of orbital chaos, and a massive shower of icy comets rained down upon our planet, melting upon impact and slowly filling the ocean basins. For a long time, this was the standard model taught in planetary science, but science demands more than elegant narratives. It requires physical proof. To verify the comet hypothesis, researchers needed to apply the rigorous isotopic fingerprinting method they had developed. They needed to measure the ratio of heavy deuterium to standard hydrogen inside a comet and compare it against the established baseline of Earth's oceans. Acquiring this data required some of the most daring feats of orbital engineering in human history. In 1986, the European Space Agency directed the Giotto spacecraft to fly directly through the chaotic, debris-filled coma of Halley's Comet. It was the first time humanity tasted the chemical makeup of an icy nomad from deep space. Decades later, the Rosetta mission achieved an even more astonishing milestone by orbiting and deploying a lander directly onto the surface of Comet 67 P. Churyumov-Gerasimenko. Aboard these spacecraft were highly sensitive mass spectrometers designed specifically to inhale the outgassing vapor of the comet and count the individual isotopes of hydrogen. When the telemetry from these missions finally reached Earth, the results sent shock waves through the planetary science community. The isotopic fingerprint of the water pouring off these comets did not match our oceans. It was not even close. The data revealed that the water locked inside Halley and Comet 67P contained a drastically higher concentration of deuterium than the water found anywhere on Earth. In many cases, the ratio of heavy hydrogen to normal hydrogen in these cometary bodies was double or even triple the standard ocean baseline. Remember the fundamental rule of isotopic sorting from the protoplanetary disk. A higher deuterium ratio means the water ice formed in an infinitely colder environment far beyond the regions where Earth's building blocks were assembled. The water on these comets was fundamentally, chemically incompatible with the water flowing in our rivers and deep seas. This leads to a profound scientific consequence. While comets absolutely struck the early Earth and undoubtedly delivered some moisture, the hard mathematical reality of the isotopic mismatch means they could not possibly be the primary source of our oceans. Even under the most generous orbital bombardment models, planetary geochemists calculate that comets could have contributed 10% of Earth's total water budget at the absolute maximum. If you tried to fill the Pacific Ocean entirely with melted cometary ice, the overall deuterium ratio of our planet would be vastly higher than what we observe today. At a planetary scale, the collapse of the comet hypothesis completely changes our understanding of how terrestrial worlds become habitable. If the vast, icy reservoirs of the outer solar system are not the primary donors of water, then creating a wet planet is far more difficult and mechanically complex than simply waiting for a random meteor shower from the Oort cloud. And right here, this failed hypothesis connects with a much larger question regarding the frequency of life in the universe. In the search for extraterrestrial intelligence, scientists often look for rocky planets sitting in the habitable zones of other stars. We used to assume that as long as a star system had an outer belt of comets, those inner rocky worlds would eventually get watered. But the isotopic failure of comets in our own solar system suggests that this simple transport mechanism does not work. This implies a terrifying potential reality for astrobiology. The universe might be filled with billions of rocky planets sitting at the perfect temperature to support liquid water, but they remain permanently sterile. Dry deserts because the comets that struck them simply bounced off, vaporized, or possessed the wrong chemical makeup to form lasting oceans. The delivery of water requires a much more specific, perhaps much rarer, mechanism. If the icy nomads of the deep dark did not bring the oceans to us, the entire scientific community was forced to abandon the outer solar system. The investigation had to pivot. The detectives of cosmic history began looking closer to home, focusing their instruments on a much darker, much drier class of ancient debris floating just beyond the orbit of Mars. With comets mathematically exiled from the investigation, the search for our oceans shifted violently inward, stopping just past the orbit of Mars. Here lies the main asteroid belt, a chaotic ring of failed planetary building blocks. For decades, astronomers viewed this region as a graveyard of dry, dead rock. But within this rubble field exists a specific class of ancient debris known as carbonaceous chondrites. These are not the bright, reflective snowballs of the outer solar system. They are pitch black, heavily cratered stones representing some of the most primitive, unaltered material in the entire universe. At first glance, a carbonaceous asteroid appears entirely devoid of moisture. If you strike one with a hammer, it shatters into dry dust, but the secret to their oceans is hidden at the molecular level. The moisture is not trapped as ice lying in dark craters. It is chemically baked into the very crystal lattice of the rock itself. Through a process called aqueous alteration that occurred billions of years ago in the early solar nebula, individual water molecules bonded directly with silicate minerals to form clays, known scientifically as phyllosilicates. If you take a fragment of a carbonaceous chondrite and heat it in a laboratory vacuum, the rock literally begins to sweat. The extreme heat breaks the chemical bonds within the crystal lattice, releasing pure water vapor. Measurements reveal that some of these dark asteroids consist of up to 20% water by mass. They are essentially flying, petrified oceans. The moment cosmic chemists analyzed the vapor outgassing from these meteorites, the isotopic puzzle finally snapped into place. When scientists measure the ratio of heavy deuterium to standard hydrogen in carbonaceous chondrites, it aligns perfectly with the standard mean ocean water baseline of Earth. To ensure this was not a statistical anomaly, researchers cross-referenced a second chemical fingerprint measuring the ratio of heavy nitrogen to standard nitrogen. Once again, the precise signature of the dark asteroids perfectly mirrored the nitrogen profile found within our atmosphere and deep mantle. The chemical conviction was absolute. These dark, primitive rocks were the undeniable donors of our oceans. But this discovery immediately birthed a severe mechanical paradox. Carbonaceous chondrites primarily reside in the outer, colder edges of the main asteroid belt, safely beyond the snow line where they originally coalesced. Earth is situated deep inside the hot inner solar system. In the frictionless vacuum of space, an asteroid does not simply change its orbit without reason. For trillions of tons of waterlogged rock to suddenly fall toward the sun and strike the early Earth, a catastrophic gravitational disruption was required. A delivery system of unimaginable scale had to activate. This brings us to a revolutionary concept in orbital dynamics known as planetary migration. We are accustomed to visualizing our solar system as a stable, clockwork mechanism, with planets spinning in permanent, unchanging tracks. But early in its history, the architecture of the solar system was highly fluid and violently unstable. According to advanced dynamical models, the gas giants did not remain where they were initially born. Jupiter, possessing immense gravitational mass, began to spiral inward, drifting closer and closer to the Sun, plowing directly through the primordial asteroid belt. As Jupiter bulldozed its way inward, its massive gravitational wake acted like a cosmic centrifuge. It scattered the dry, metallic asteroids of the inner belt outward into the cold dark. Simultaneously, it grabbed the water-rich, carbonaceous chondrites from the outer belt and hurled them violently inward toward the Sun. Just as Jupiter threatened to migrate too far and completely consume the inner rocky planets, the gravitational pull of a newly formed Saturn caught it. The two massive planets locked into a resonant gravitational dance that yanked Jupiter back out to its current stable orbit. This inward and outward sweeping motion essentially churned the entire solar system. Earth was caught directly in the crossfire of this gravitational churning, as billions of carbonaceous asteroids were thrown into the inner solar system. Our nascent planet intercepted a massive portion of them. This was not a gentle accumulation of moisture. It was a prolonged apocalyptic bombardment of dark, heavy rocks slamming into the young, molten Earth. The kinetic energy of these impacts repeatedly shattered the planetary crust, but the sheer volume of the delivery overwhelmed the heat. As the rocks melted and integrated into Earth's deepening mantle, their chemically bound water was released, eventually outgassing through global volcanism to condense into the very first true oceans. At a planetary scale, the meaning of this mechanism changes entirely, shifting our understanding of how rare a wet planet might truly be. We have long considered gas giants like Jupiter to be protective shields, sweeping up dangerous debris to keep Earth safe from impacts. But the planetary migration model reveals a far more complex reality. Jupiter was not just a shield, it was the active, violent delivery mechanism that forced the water to cross the snowline. And exactly here, this dynamical requirement begins to connect with the ultimate question regarding the longevity of any technological civilization. If the delivery of oceans requires a gas giant to migrate inward, scatter specific carbonaceous asteroids, and then be pulled back just in time by a second gas giant before destroying the inner system, we are looking at a terrifyingly specific sequence of events. When we observe exoplanetary systems across the galaxy, we see many gas giants that simply kept migrating inward, becoming scorching hot worlds that incinerated their rocky neighbors. We see others that never migrated at all. If this chaotic gravitational dance is an absolute prerequisite for moving water into the habitable zone, it functions as a profound great filter. The vast majority of rocky planets in the universe may remain permanently dry, not because they lack the raw materials, but because their solar systems lack the precise gravitational choreography to deliver them. The existence of liquid oceans on Earth might not be a chemical inevitability, but rather the exceptionally lucky outcome of a chaotic orbital ballet that rarely plays out exactly right twice. While the chaotic migration of gas giants provides a compelling mechanism for water delivery, modern astrophysicists remain deeply uncomfortable relying on cosmic accidents. The planetary migration model requires an exquisitely timed sequence of gravitational events. If Jupiter had migrated slightly too fast, or if Saturn had formed slightly too late, Earth would have been either entirely pulverized or left permanently completely bone dry. In physics, whenever a foundational property of a system relies on incredibly narrow margins of luck, it usually means our theoretical models are incomplete. Scientists began to ask a more profound question. What if the delivery of oceans is not the result of a rare, catastrophic asteroid bombardment, but rather a fundamental, inescapable law of fluid dynamics operating in every young star system? In recent years, a quiet revolution has taken place in planetary formation theory. Advanced supercomputer simulations capable of tracking the aerodynamic behavior of individual particles in a solar nebula have birthed a radically different framework known as the Pebble accretion model. To understand this paradigm shift, we must zoom in on the microscopic mechanics of the outer protoplanetary disk, far beyond the freezing boundary of the snow line. In the deep cold of the outer system, microscopic silicate dust grains do not merely float in isolation. They become instantly coated in thick mantles of frozen water, ammonia, and carbon monoxide. This icy outer layer fundamentally changes the physical properties of the dust. Ice is incredibly sticky. When these microscopic, frost-covered grains collide in the swirling nebula, they do not shatter and bounce apart like dry rocks. They adhere to one another, rapidly coagulating into larger and larger structures. Within a mere few thousand years, an incredibly short span in cosmic terms, this process generates trillions upon trillions of small, icy aggregates ranging from the size of a marble to a baseball. Planetary scientists refer to these objects simply as pebbles, but these icy pebbles do not stay in the outer solar system. They are subjected to a relentless aerodynamic force. The early solar nebula was not an empty vacuum. It was a dense, rotating fluid of hydrogen and helium gas. Because this gas is slightly supported by its own internal outward pressure, it orbits the young sun at a velocity just below the standard Keplerian speed required for solid objects. This creates a permanent, severe headwind. As the icy pebbles race around the sun, they constantly smash into this slower-moving gas. The aerodynamic drag saps their orbital energy, causing their angular momentum to steadily decay. The result is a massive, system-wide inward spiral. A relentless, continuous blizzard of icy material begins to drift from the freezing outer reaches directly toward the blazing inner solar system. As this endless stream of frozen pebbles crosses the snow line and enters the hot, rocky domain where Earth was actively forming, the physics of planetary construction change completely. Classic models assumed that planets grew slowly by smashing massive dry boulders into one another. But pebble accretion suggests that a young, growing planetary embryo acts more like an aerodynamic filter. As the icy pebbles sweep past the nascent Earth, they enter its gravitational well. Because the pebbles are still fighting the friction of the surrounding nebular gas, they are forcefully decelerated right as they pass the planet. This precise combination of gravity and aerodynamic drag allows the young Earth to sweep up phenomenal quantities of material with ruthless efficiency. However, this model immediately presents a severe thermal contradiction. As these pebbles drift inward past the snow line, the increasing solar heat should cause their icy mantles to rapidly sublimate, transforming the frozen water directly into vapor before it ever reaches the young Earth. But the physics of mass transfer reveal a different reality. The sheer volume of the inward drifting pebbles is so astronomically vast that it alters the local humidity of the solar nebula. The sublimating water vapor forms a dense, protective envelope around the innermost drift streams, shielding the remaining icy pebbles from complete evaporation. Furthermore, the young Earth was accumulating this material at such a violent, rapid pace that the icy pebbles were immediately buried deep beneath layers of falling silicate rock. This leads to a profound shift in our understanding of planetary history. Under the asteroid bombardment model, Earth was fully constructed as a dry, dead sphere, and the water was delivered later, forming a superficial layer on the surface. But the pebble accretion model rewrites this timeline entirely. It implies that Earth was actively swallowing colossal quantities of frozen water during the exact same period it was building its iron core and rocky mantle. The water was not an afterthought. It was a foundational building block. Earth did not become wet. It was born wet. The moisture was locked deep inside the planetary interior from the very first moments of its existence, boiling within the primordial magma ocean. At a planetary scale, the meaning of this continuous aerodynamic drift alters our entire perspective on the cosmos. If water delivery is driven by the basic fluid dynamics of gas drag and sticky icy dust, then it is not a rare anomaly. It is a universal mechanical default. Every single protoplanetary disk currently spinning around a young star in our galaxy is subject to these exact same aerodynamic laws. And precisely here, this elegant physical model connects directly to the search for extraterrestrial intelligence. If pebble accretion is the dominant mechanism for planet building, it essentially guarantees that rocky worlds situated in the habitable zones of other stars are continuously seeded with water directly from their outer ice belts. The chemical bottleneck disappears. The universe should theoretically be overflowing with ocean worlds. If we accept that the raw materials for life are delivered so efficiently by the fundamental architecture of solar systems, the terrifying silence of the cosmos becomes even more deafening. If water is ubiquitous, then the great filter preventing the rise of alien civilizations does not lie in the chaotic delivery of oceans. It must lie somewhere else, perhaps in the infinitely more complex challenge of keeping those oceans stable, or in the fragile biological leaps required to utilize them. If we accept the premise that Earth was actively accumulating water from an endless drift of icy pebbles, or sweeping up dark asteroids during its infancy, we run headfirst into one of the most violent contradictions in planetary science. Roughly 4.5 billion years ago, just as the early Earth had nearly finished assembling itself, its entire physical structure was fundamentally unmade. A rogue protoplanet, roughly the size of Mars and generally referred to as Theia, collided with our young world at an oblique angle. The kinetic energy released by this impact is nearly beyond human comprehension. It did not merely crack the crust, it completely liquefied both planets. The immediate aftermath was an apocalyptic restructuring of our world. A massive volume of vaporized debris was blasted into planetary orbit, which eventually coalesced to form the Moon. Meanwhile, the entire surface of the Earth melted into a global magma ocean, plunging thousands of miles deep, all the way down to the metallic core. By all classical laws of thermodynamics, this catastrophic thermal event should have been the end of Earth's water story. When silicate rock is subjected to temperatures exceeding 4,000 degrees Fahrenheit, any volatile compounds trapped within it should instantly vaporize. If early Earth was a wet planet, the thermal shock of the Theia collision should have instantly boiled its primitive oceans. The resulting water vapor, superheated and accelerated by the explosive force of the impact, should have easily achieved escape velocity and been permanently lost to the vacuum of space. According to standard models, the formation of the Moon should have sterilized Earth, leaving it an entirely desiccated, bone-dry sphere of cooling rock. Yet, we are still here, living on a blue planet. To resolve this terrifying paradox, modern geochemists had to look deep into the field of high-pressure mineral physics. The solution lies in the counterintuitive behavior of water when it is subjected to immense geological crushing forces. Water does not simply boil away when it is buried under millions of tons of liquid rock. Deep within the global magma ocean, at pressures thousands of times greater than what we experience at sea level, the chemical rules change. Under these extreme conditions, water molecules do not form bubbles of steam. Instead, they are forcefully fractured and dissolved directly into the molten silicate lattice. The magma ocean acted like a planetary scale sponge, chemically binding the hydrogen and oxygen atoms within the structure of the liquid rock itself. As the very top layer of this magma ocean interacted with the cold vacuum of space, it began to cool and outgas, releasing some of its trapped volatiles. This created an incredibly dense, crushing, opaque atmosphere composed primarily of supercritical steam and vaporized rock. But this atmosphere did not simply drift away. Because Earth retained the vast majority of its mass after the collision, its immense gravitational field held this steam envelope tightly against the planet. This leads to a fascinating mechanical effect. The sheer weight of this towering steam atmosphere exerted an unimaginable downward pressure on the boiling surface of the magma ocean. It functioned exactly like the lid of a pressure cooker. The immense atmospheric pressure physically prevented the deeper, dissolved water from rising to the surface and outgassing. While the uppermost layers of the planet were losing moisture to space, the vast reservoirs of water trapped deep in the lower mantle were chemically locked in place, protected by the crushing weight of the sky above them. But the problem does not stop at mere retention. Recent isotopic modeling presents a radical alternative that flips the entire narrative of the Theia impact. What if Theia was not just a dry rock acting as a destructive hammer, but rather a massive carbonaceous protoplanet originating from the cold outer solar system? In this compelling scenario, Theia was the ultimate delivery vehicle. Instead of Earth slowly sweeping up billions of tiny icy pebbles over millions of years, a single water-rich world slammed into us, depositing an entire oceanic payload directly into the planetary interior in one catastrophic moment. This bold hypothesis is heavily supported by the terrifyingly identical isotopic fingerprints shared by Earth and the Moon. When Apollo astronauts brought lunar rocks back to laboratories, geochemists discovered that the oxygen, titanium, and tungsten isotopes of the Moon are virtually indistinguishable from those of Earth's mantle. This level of chemical homogeneity suggests that, after the impact, Earth and Theia did not just shatter, they completely vaporized and mixed together into a spinning donut-shaped cloud of boiling rock and superheated fluid, a theoretical structure known as a synestia. Within the extreme blender of a synestia, the water from Theia would have thoroughly mixed with the material of the early Earth before the planet cooled and recondensed into a solid sphere. This perfectly explains why the isotopic signature of Earth's deep mantle is so uniform today. At a planetary scale, the meaning of this violent collision changes entirely, forcing us to reevaluate our assumptions about how habitable worlds are forged. We inherently view giant impacts as planetary destroyers, apocalyptic events that end worlds. But in the context of astrobiology, this specific catastrophic collision might be the ultimate prerequisite for long-term habitability. If Earth had not been struck by Theia, it might have retained a massive, crushing primordial atmosphere of hydrogen and helium gas, turning it into a sterile sub-Neptune planet where the surface pressure is far too high for complex chemistry to thrive. Alternatively, without the impact to blow off the excess, Earth might have retained too much water from the pebble accretion phase. It could have become a deep water world, a planet completely submerged under an ocean hundreds of miles deep, where the immense pressure at the sea floor forms a permanent barrier of exotic, high-pressure ice, completely cutting off the chemical cycling between the rock and the water that is absolutely necessary for the genesis of biological life. The Theia impact stripped away the suffocating primary atmosphere, violently boiled off the dangerous excess of water, and forcefully injected precisely the right amount of moisture deep into the planetary interior. This delicate, almost impossible balance of destruction and retention leaves us with a profound realization regarding our place in the universe. The habitability of our world and the very existence of our oceans relies on a catastrophic near-death experience. And precisely here, this understanding of high-pressure magma retention begins to connect with a much larger question. If the global magma ocean acted as a sponge, locking water into the cooling rock, it implies that the true scale of Earth's water is hidden far from the sunlight, setting the stage for a completely different kind of ocean. Up to this point, every major scientific model we have examined shares one fundamental, deeply ingrained assumption. Because the inner solar system was a violent thermal furnace, the raw materials that built the Earth were absolutely, fundamentally dry. We assumed that water had to be a late arrival, a cosmic import delivered by icy nomads, migrating gas giants, or drifting frozen pebbles from beyond the snow line. But what if this entire premise is flawed? What if we have been looking toward the outer darkness for decades, completely missing a profound mechanism operating right beneath our feet? To challenge the exogenous delivery model, geochemists turned their attention away from the dark, water-rich rocks of the outer asteroid belt and focused on a much rarer class of meteorites known as enstatite chondrites. These rocks are the true natives of the inner solar system. They coalesced out of the primordial dust right here, perfectly within the scorched zone where the Earth itself was forming. For over a century, planetary scientists classified enstatite chondrites as the driest objects in the cosmos. Because they formed so close to the stellar furnace, they are highly reduced, meaning they contain almost no oxidized iron, and were seemingly stripped of all volatile compounds. If you bake a rock at over 2,000 degrees near a young protostar, basic thermodynamic logic dictates that no moisture can possibly survive. However, the steady march of technological progress continuously shatters our most basic assumptions. When modern mass spectrometry instruments finally achieved the sensitivity to probe the atomic lattice of these ancient rocks at the parts per million level, a stunning chemical reality was revealed. The enstatite chondrites were not perfectly dry. They did not contain ice crystals, and they did not contain chemically bound water molecules like their carbonaceous cousins from the outer solar system. Instead, they contained trace amounts of pure unbonded hydrogen atoms, wedged deeply within the microscopic structural defects of their mineral matrix. The concentration was incredibly minute, ranging from merely 1/100th to 1/10% by weight. To a casual observer, a rock containing 1/10% hydrogen is still a dry rock. But at a planetary scale, the meaning of this trace element changes entirely. Planetary formation is a game of unimaginable mass. If you construct an entire planet the exact size of Earth using these seemingly dry native enstatite chondrites, that microscopic fraction of hydrogen begins to multiply. When geochemists calculated the total hydrogen inventory of a planet built entirely from these rocks, the mathematical result was staggering. The trace amounts locked inside the local building blocks were sufficient to produce at least 3 times the total volume of water currently residing in all of Earth's surface oceans combined. But a trapped gas is not an ocean. To transform this scattered atomic hydrogen into the liquid biosphere we recognize, a massive chemical conversion was required, and right here, the violent molten state of the early Earth becomes the necessary catalyst. As the primordial planet aggregated and melted into a global magma ocean, the solid enstatite rocks dissolved. The trace hydrogen atoms were suddenly liberated into a swirling, high-pressure bath of liquid silicate magma. Silicate rocks, by their very nature, are overwhelmingly composed of oxygen. In the extreme heat and crushing depth of the deep mantle, the freed hydrogen atoms violently bonded with the abundant oxygen stripped from the molten rock. The Earth did not wait for water to be delivered from the cold void. It actively manufactured it. It forged its oceans from the inside out, essentially sweating out the water as a byproduct of its own geological cooling process. This endogenous model solves one of the most frustrating forensic headaches in modern planetary science. While carbonaceous asteroids from the outer solar system share Earth's deuterium to hydrogen ratio, they fail in other critical isotopic markers. Their calcium, titanium, and chromium isotopes do not match the Earth. But the native enstatite chondrites are a flawless isotopic match across the board. They share the exact same nuclear fingerprint as the Earth and the Moon, proving definitively that they are the primary building materials of our world. If this endogenous hypothesis holds true, it does not just rewrite the deep history of our own blue world. It leads to a profound, universe-altering consequence. We have spent decades looking at the night sky, assuming that a wet planet requires a miraculous, highly improbable sequence of orbital events. We thought you needed a Jupiter to throw icy asteroids inward, or a continuous, perfectly timed stream of frozen pebbles to cross the snow line without vaporizing in the stellar wind. But the enstatite chondrite model obliterates those complex mechanical requirements. It suggests that water is not a rare cosmic import dependent on luck. It is a standard, automated feature of planetary assembly. If the raw, baked rocks of the inner solar system naturally harbor enough trace hydrogen to spontaneously generate deep oceans during the magma phase, then the snowline paradox is completely dismantled. Any rocky planet, orbiting any star across the galaxy, coalescing within the warm, habitable zone, will inherently possess the exact same trace hydrogen and oxygen chemistry. They will all bake their own water from the inside out. And precisely here, this geological revelation connects directly to the terrifying silence of the Fermi paradox. If planetary systems do not need a perfect, lucky comet strike or a chaotic gas giant migration to become habitable, then the universe should be literally teeming with warm, oceanic worlds. Water is not the great cosmic bottleneck we assumed it was. If oceans are an automated default of basic physics and chemistry, yet we still see no evidence of galactic civilizations, the implications are profound. It means the great filter preventing the spread of intelligent life does not lie in the astrophysics of planetary formation or the delivery of water. The insurmountable barrier must reside further down the timeline, waiting quietly for biological life long after the oceans have already cooled. Even as the Insta-tight chondrite model proves that the building blocks of our planet contain trace amounts of hydrogen, planetary geochemists have recently uncovered evidence pointing to a third, even more primordial source of water. This discovery forces us to look past the solid rocks and asteroids entirely and focus directly on the ghost of the solar nebula itself. When we envision the formation of Earth, we tend to picture a chaotic billiards game of colliding rocks, asteroids, and drifting icy pebbles. But we often forget the medium in which this violence took place. For the first few million years of our solar system, the space between the planets was not a vacuum. It was filled with a dense, swirling cloud of gas, overwhelmingly composed of molecular hydrogen and helium. This was the original, unprocessed stellar material left over from the collapse of the molecular cloud. As the infant Earth grew, its accumulating mass generated a formidable gravitational well. Long before the Sun ignited with enough ferocity to blow the solar nebula away, our young, molten planet was massive enough to actively inhale the surrounding space. It pulled in a thick, suffocating primary atmosphere composed almost entirely of pure nebular hydrogen. Below this crushing gas envelope, the entire surface of the Earth was a churning, global ocean of liquid silicate magma. The physical boundary between the hydrogen atmosphere and the magma ocean was not a solid line. Under the immense barometric pressure of the early atmosphere, the hydrogen gas was forced directly into the liquid rock. In the extreme heat, gas becomes highly soluble. The magma ocean acted as a planetary-scale solvent, absorbing the raw hydrogen of the cosmos directly into its molten currents. But the mechanism goes deeper. During this exact same epoch, Earth was undergoing planetary differentiation. The heaviest elements, primarily molten iron and nickel, were sinking through the silicate mantle to the center of the planet to form the core. As this liquid iron descended, it acted as a chemical dragnet. Iron, under extreme pressure, has a high affinity for hydrogen. Millions of tons of nebular hydrogen were pulled down into the deepest, most inaccessible vault of the planet, settling at the core mantle boundary nearly 2,000 miles beneath the surface. Once the iron core sealed, that hydrogen was permanently locked away. In the mantle above, the remaining dissolved hydrogen violently stripped oxygen atoms away from the liquid silicate rock, automatically synthesizing pure water deep underground. For decades, this concept of nebular ingathering was treated merely as an elegant mathematical hypothesis. Proving that our water came directly from the original gas cloud of the Sun seemed impossible, because hydrogen is highly reactive and constantly swaps bonds. To prove the theory, scientists needed to find a tracer, a chemical witness that entered the magma ocean alongside the hydrogen but refused to react with anything. They needed to find primordial noble gases. The ultimate smoking gun in this investigation is an incredibly rare isotope known as helium-3. Unlike standard helium, helium-3 is a direct relic of the Big Bang and the original solar nebula. It does not chemically bond with other elements, and it is so light that if it reaches the surface of the Earth, it immediately escapes the atmosphere and is lost to space forever. Therefore, if we detect helium-3 actively venting from the Earth today, it cannot be recycled material. It must be leaking from a deep, ancient, undisturbed reservoir that has survived intact since the birth of the planet. And we have found it. Geochemists have traveled to the most active, deep-rooted volcanic hotspots on Earth, specifically the islands of Hawaii and Iceland. Unlike the shallow volcanoes of the Pacific Ring of Fire, which erupt recycled crustal rock, the volcanic plumes beneath Hawaii and Iceland drag material upward from the absolute bottom of the mantle, right at the boundary of the iron core. When scientists capture the volcanic gases venting from these deep plumes, they consistently detect distinct, undeniable traces of helium-3 and primitive neon isotopes. The isotopic fingerprint of these noble gases does not match the signature of carbonaceous asteroids, nor does it match the enstatite rocks of the inner solar system. It matches the exact chemical spectrum of the solar wind. It is a pure sample of the original stellar nebula. The presence of these gases proves definitively that the global magma ocean directly inhaled the raw primordial gas of the solar system, and that a vast reservoir of that material is still trapped in the deep interior today. Earth did not just wait for rocks to deliver water. It drank directly from the cloud that birthed the sun. This leads to a profound cosmological consequence. The process of nebular ingathering is entirely driven by gravity, gas pressure, and magma solubility. It requires no special asteroid bombardment or lucky orbital migration. If this mechanism is true, then any rocky planet in the universe that grows large enough, fast enough, while its parent star's gas disk is still present, will automatically inhale a hydrogen atmosphere and dissolve it into its magma. The chemical synthesis of water is a thermodynamic inevitability across the galaxy, but this universal mechanism reveals a terrifying double-edged sword, linking directly to the concept of the Great Filter. While inhaling nebular gas provides the essential hydrogen for oceans, inhaling too much of it is biologically catastrophic. When astronomers observe exoplanetary systems, one of the most common types of planets they find are sub-Neptunes. These are rocky worlds, slightly larger than Earth, that formed quickly and gathered a massive, crushing envelope of hydrogen and helium gas. If a rocky planet fails to shed this primary atmosphere, the atmospheric pressure at the surface becomes so astronomically high that any water present is instantly compressed into exotic, high-pressure ice, even at boiling temperatures. The rocky surface is permanently sealed off from the liquid water by an impenetrable wall of hot ice, completely preventing the chemical weathering and mineral cycling that are absolutely required for the genesis of life. Earth managed to thread a nearly impossible cosmic needle. It grew fast enough to inhale the necessary hydrogen from the nebula, but it grew slowly enough, and the young sun's stellar winds were fierce enough to blow away the crushing gas envelope before it permanently choked the planet. Our world was left with just the right amount of hydrogen dissolved in the rock and a stripped atmosphere that allowed that hydrogen to eventually outgas as liquid oceans. And precisely here, the detection of solar nebula gases leaking from the core mantle boundary begins to connect with a much larger question. If the deep mantle of the Earth holds the chemical relics of the solar cloud, and if the early magma ocean acted as a giant planetary sponge absorbing oceans' worth of hydrogen, where is all that water now? The global ocean we see on the surface might merely be a puddle compared to the dark, pressurized seas locked far beneath our feet. When we look at a globe, the Pacific and Atlantic appear unimaginably vast. But compared to the total volume and mass of the Earth, our surface oceans are nothing more than a microscopic film of condensation clinging to the outermost crust. If the violent magma ocean of the early Earth acted as a planetary sponge, absorbing hydrogen directly from the solar nebula and capturing water from thousands of carbonaceous impacts, then the surface water we see today cannot possibly represent the whole story. The mathematics of planetary accretion simply do not balance out. There had to be a hidden reservoir. To find the missing water, geologists had to look far beneath the seabed, probing a mysterious high-pressure layer of the deep interior known as the mantle transition zone, located roughly 250 to 400 miles below our feet. Down in the extreme environment of the transition zone, the fundamental definition of water changes entirely. We are accustomed to experiencing water in three distinct everyday phases, as a flowing liquid, solid, ice, or gaseous vapor. But at the crushing depths of the deep mantle, under pressures exceeding hundreds of thousands of times our standard surface atmosphere, water cannot physically exist in any of those familiar forms. Instead, it undergoes a radical chemical transformation. The immense geological pressure forces the hydrogen and oxygen atoms to split and integrate directly into the atomic architecture of the surrounding rock. The water becomes an intrinsic part of the crystal lattice itself, existing as trapped hydroxyl ions. The rock in this region is completely solid, glowing white-hot, yet chemically it is absolutely drenched. This deep storage mechanism is governed by two extremely specific high-pressure minerals called wadsleyite and ringwoodite. These are essentially highly compressed, polymorphic versions of olivine, the common green mineral that makes up the vast majority of Earth's upper mantle. Because of the unique, complex way their atomic structures fold under extreme pressure, both wadsleyite and ringwoodite become highly accommodating at a subatomic level. They act like molecular sponges, capable of soaking up to nearly 2% of their total weight in hydrogen and oxygen. While 2% might sound like an insignificant fraction, you have to multiply that trace amount by the incomprehensible planetary scale volume of the entire global transition zone. When geophysicists run the numbers on this subterranean mineral layer, the results completely dwarf the surface world. The transition zone holds such an immense volume of rock that, even at a mere 1% hydration level, it contains the equivalent mass of 1 to 3 entire surface oceans. There is vastly more water locked inside the solid, burning rock of the deep Earth than there is splashing against all the coastlines on the surface combined. For a long time, however, this internal ocean was strictly a mathematical theory. We cannot simply drill 400 miles into the Earth to take a physical sample. The deepest artificial hole ever dug by human engineering barely scratches the outermost continental crust. To prove the existence of this hidden reservoir, science required an indirect messenger. The first major clues came from global planetary seismology. When massive earthquakes send powerful seismic waves echoing through the interior of the planet, geophysicists can measure their speed and trajectory. As these shock waves hit the transition zone, they consistently slow down in specific, widespread regions. In the physics of high-pressure geology, a decelerating seismic wave is the definitive, undeniable signature of wet rock. But the ultimate physical proof was delivered to the surface completely by accident, trapped inside a diamond. Originating deep within the mantle, an ultra-rare, incredibly resilient diamond was violently propelled to the surface by a deep-rooted volcanic eruption in Brazil. Trapped inside its flawless carbon matrix was a microscopic flaw, a tiny grain of primordial ringwoodite that had been perfectly sealed and protected from the decompression of its journey. When researchers analyzed this microscopic inclusion using advanced infrared spectroscopy, that deep earth mineral was confirmed to contain a massive concentration of hydroxyl ions. It was a perfectly preserved drop of the subterranean ocean carried up from the abyss to prove the models correct. At a planetary scale, the meaning of this deep reservoir changes our entire perspective on what constitutes a habitable world. We currently define the search for extraterrestrial life by aggressively looking for planets with liquid water oceans pooling on their surfaces. But the ringwoodite discovery reveals a profound astrobiological reality. A planet's true water budget is actually hidden inside its rock. When we use space telescopes to observe a seemingly dry, dead exoplanet, or even a neighboring rocky world in our own system, we might be looking at a planetary structure that simply absorbed all of its water internally. A surface ocean is not the primary reservoir. It is merely a temporary, fragile overflow of a much larger internal geological system. And exactly here, this deep mantle storage capacity connects with the terrifying question of civilizational longevity and the Great Filter. If an ocean is simply an exposed overflow, it is incredibly vulnerable. It can be boiled away by an expanding star, stripped by solar winds, or frozen solid by orbital shifts. A rocky world needs an internal buffer, a deep battery of moisture to constantly replenish the surface over billions of years. Without the massive hidden storage capacity of the Wadsleyite and Ringwoodite crystal lattices, Earth's surface water might have permanently dried up eons ago, turning our world into a sterile, desiccated desert long before complex biology ever had a chance to evolve. But an internal reservoir is utterly useless for sustaining life if it remains permanently locked away in the dark. For the surface biosphere to survive, the solid rock of the planet must have a mechanism to breathe. The deep Earth must somehow cycle that hidden ocean back into the sky. Having billions of tons of water trapped inside the deep mantle, crystal lattice of Ringwoodite is a staggering geological marvel. But from the perspective of biology, an entirely isolated underground reservoir is completely useless. If the water remains permanently locked in the dark hundreds of miles below the crust, the surface world would eventually succumb to atmospheric loss and turn into a sterilized, desiccated desert. For an ocean to actively sustain complex life, drive climate systems, and stabilize the atmosphere, the solid rock of the planet must have a mechanism to breathe. There must be a mechanical connection between the abyss and the sky. This brings us to the profound reality of the deep water cycle. We are all deeply familiar with the surface water cycle, where solar heat evaporates the ocean, forms clouds, and returns moisture to the land as rain. But that surface cycle is merely a rapid, fragile weather pattern. It is completely entirely dependent upon a much grander, infinitely slower planetary engine operating on a time scale of hundreds of millions of years. This grand engine is driven entirely by the relentless motion of plate tectonics. The cycle of deep hydration begins at the absolute bottom of the surface ocean, specifically along the mid-ocean ridges. These are massive underwater volcanic mountain ranges where tectonic plates are actively tearing apart. As fresh, superheated magma rises from the mantle to fill the gap, it meets the freezing water of the deep sea. The extreme thermal shock fractures the newly formed rock, creating deep fissures. Ocean water aggressively percolates down into these cracks, penetrating miles into the oceanic crust. But the water does not simply sit there. In the intense heat and pressure of the deep crust, the water chemically reacts with the iron and magnesium-rich minerals of the mantle rock. This triggers a widespread metamorphic transformation known as serpentinization. The rock physically expands, changes color, and binds the water molecules directly into its mineral structure. The entire ocean floor essentially transforms into a slow, moving, planetary scale sponge, soaking up massive volumes of the sea. But the ocean floor is not stationary. It acts as a colossal conveyor belt. Over tens of millions of years, this waterlogged oceanic crust is pushed away from the mid-ocean ridge, traveling across the globe until it collides with a thicker, more buoyant continental plate. At this violently contested boundary, the heavier oceanic crust is forced downward, plunging back into the deep interior of the planet. This process is called subduction. The deep ocean trenches of our world, like the Mariana Trench, are not just dark canyons. They are literal planetary drains. Through subduction, the Earth is actively swallowing its own oceans, dragging millions of tons of chemically bound water down into the crushing depths of the mantle every single year. If this descending mechanism operated completely unchecked, the surface oceans of the Earth would have been entirely drained into the interior billions of years ago. To prevent the surface from drying out, the planet requires an equally powerful mechanism to push the water back up. As the saturated oceanic plate dives deeper into the mantle, it is subjected to rapidly intensifying heat and unimaginable geological pressure. Eventually, the descending slab reaches a critical thermal boundary. The high-pressure minerals within the rock become violently unstable. The crystal lattice structurally collapses, and the trapped water is forcefully expelled back into the surrounding environment in a process known as dehydration. This leads to a fascinating and highly destructive chemical reaction. When pure superheated liquid water is injected into the scorching solid rock of the overlying mantle wedge, it acts as a chemical flux. Just as throwing salt onto an icy road lowers the melting point of the ice, injecting water into the deep mantle drastically lowers the melting point of the rock. The solid mantle instantly liquefies, generating colossal plumes of buoyant, volatile, rich magma. This newly formed magma is significantly lighter than the surrounding rock, and it begins a relentless journey upward, burning its way through the continental crust. When this magma finally breaches the surface, the sudden release of pressure causes the dissolved water to rapidly expand into vapor, driving explosive volcanic eruptions. The massive stratovolcanoes that line the Pacific Ring of Fire are not merely mountains of fire. They are the highly pressurized exhaust pipes of the planetary engine. Every time a volcano erupts, it is outgassing massive columns of steam, actively returning the deep trapped water back to the atmosphere, where it eventually cools, condenses, and falls as rain to replenish the oceans. At a planetary scale, the meaning of this deep cycle alters our entire understanding of planetary stability. The volume of the Earth's oceans is not a static number determined at the birth of the solar system. It is a dynamic, shifting equilibrium. The surface ocean is perfectly balanced on a knife edge between the rate of tectonic subduction pulling water down and the rate of volcanic outgassing pushing water back up. If the subduction conveyor belt runs too fast, the planet dries out. If the volcanic outgassing accelerates too rapidly, the planet floods, potentially creating a runaway greenhouse effect from the excess water vapor. The fact that Earth has maintained a stable, liquid ocean for over 4 billion years is a testament to the exquisite self-regulating balance of this tectonic engine. And precisely here, this geological mechanism connects directly with the ultimate question of astrobiology and the Great Filter. When we look at our neighboring planets, we see the apocalyptic consequences of a broken water cycle. Mars, being much smaller than Earth, cooled down too rapidly. Its internal tectonic engine stalled. Without active volcanoes to outgas moisture, whatever surface water it possessed was either lost to space or permanently trapped underground. Venus suffered a different failure, likely experiencing a completely stagnant lid tectonic regime where water could not be effectively cycled, contributing to its transformation into an atmospheric inferno. If plate tectonics and this deep, continuous water cycle are absolute prerequisites for maintaining a stable surface ocean over geological timescales, it severely limits the number of habitable worlds in the galaxy. We can point our space telescopes at distant stars and find countless rocky exoplanets sitting at the exact right temperature. But if those alien worlds lack the internal heat and specific geological mechanics to sustain plate tectonics, their oceans will inevitably drain away or boil off. This suggests that the true barrier to long-lasting extraterrestrial civilizations is not just the initial delivery of water, but the incredibly rare, continuous planetary heartbeat required to keep that water circulating from the dark abyss to the open sky. Acquiring oceans through violent cosmic collisions, deep space pebble drift, or primal atmospheric ingathering is only the first chapter of the planetary water story. The much more difficult challenge, and the one that ultimately determines the biological fate of a world, is keeping that water. The surface of a rocky planet is not a sealed vault. It is a highly exposed boundary completely subjected to the unrelenting hostility of its host star. If a planet cannot actively defend its oceans, the universe will ruthlessly strip them away. To understand this vulnerability, we have to look at the behavior of water molecules when they are elevated into the upper atmosphere. When the sun heats the surface, water evaporates and rises as gas. Once this vapor reaches the stratosphere, it is bombarded by extreme ultraviolet radiation. This high-energy light acts as a cosmic scalpel, slicing the chemical bonds of the water molecule apart in a process known as photodissociation. The heavier oxygen atoms tend to sink back down, but the hydrogen atoms are entirely different. Hydrogen is the lightest element in the universe. Once liberated from oxygen, it gains immense thermal energy from the solar radiation vibrating and accelerating to incredible speeds. If these hydrogen atoms accelerate fast enough, they overcome the gravitational pull of the planet and bleed out into the dark vacuum of space, a mechanism called hydrodynamic escape. Every single drop of water that undergoes this process is permanently deleted from the planetary inventory because hydrogen is the fundamental building block of water. Losing it means the planet is slowly, irreversibly dehydrating. Earth possesses an immense gravitational well, which provides the first critical line of defense. The physical mass of our planet dictates a high escape velocity, meaning a gas molecule has to travel extremely fast to break free. This heavy gravity easily holds onto nitrogen, oxygen, and carbon dioxide. But hydrogen is so incredibly light and volatile that even Earth's impressive gravity cannot contain it completely. If gravity were our only shield, our oceans would have slowly boiled off into the void billions of years ago. The true protector of our blue world lies 3,000 miles beneath the ocean floor. At the very center of the Earth, a sphere of solid iron is surrounded by a churning, boiling ocean of liquid iron and nickel. As the planet rotates, the convection currents within this superheated liquid metal generate immense electrical currents. These currents, in turn, project a massive, invisible electromagnetic force field out into space. This is the geodynamo, the engine that creates the magnetosphere. This magnetic shield extends thousands of miles beyond the atmosphere, and it is the only thing standing between our fragile surface water and the sheer destructive power of the solar wind. The sun does not just emit light. It constantly detonates, blasting a continuous hurricane of charged plasma, protons, and electrons outward at 1,000,000 miles per hour. When this lethal solar wind slams into the Earth, it does not strike the atmosphere. It crashes against the invisible wall of the magnetosphere and is safely deflected around the planet, sliding off into deep space. But this is not merely a theoretical danger. To see the apocalyptic consequences of a failed planetary defense system, we only need to look at our immediate cosmic neighbors. Both Venus and Mars were born with massive reservoirs of water, perhaps even global oceans. Today, they are sterilized, desiccated wastelands. Their tragedies perfectly illustrate the fragile architecture of habitability. Mars is a smaller planet. Because it lacked sufficient mass, its internal core cooled down much faster than Earth's. As the core solidified, the geodynamo stalled, and the Martian magnetosphere collapsed. Without a magnetic shield, the naked Martian atmosphere was subjected to the full abrasive force of the solar wind. Over hundreds of millions of years, the sun literally sandblasted the atmosphere away, carrying the water vapor with it into the deep dark. Venus suffered a distinctly different, yet equally catastrophic fate. Venus possesses almost the exact same mass and gravity as Earth, but it rotates incredibly slowly, which prevents it from generating a protective magnetic field. Furthermore, Venus experienced a runaway greenhouse effect. The extreme surface temperatures caused the entire Venusian ocean to boil into the sky. With the entire water budget pushed into the upper atmosphere, the ultraviolet radiation effortlessly shattered the molecules. The solar wind swept the hydrogen away, completely dehydrating the planet. The oxygen that was left behind bonded with carbon, creating the suffocating, toxic atmosphere of carbon dioxide that crushes the Venusian surface today. Earth survives because it possesses a flawless combination of internal and external mechanics. We have the mass to hold the atmosphere, the internal heat to power the magnetic shield, and a crucial third meteorological defense mechanism known as the stratospheric cold trap. As water vapor rises from our oceans, it encounters a specific temperature inversion layer in the atmosphere called the tropopause. Here, the air temperature suddenly drops to roughly minus 60 degrees Fahrenheit. This extreme cold freezes almost all ascending water vapor into heavy ice crystals, forcing them to fall back to the surface as snow or rain before they can ever reach the dangerous high-altitude regions where ultraviolet photodissociation occurs. Earth actively locks its water in the lower atmosphere, hiding it from the solar scalpel. At a planetary scale, the meaning of these combined defenses changes our entire perspective on the search for extraterrestrial civilizations. Habitability is not a static condition, it is a violent, ongoing war against the host star. And right here, this delicate atmospheric architecture connects directly to the greatest modern challenge in astrobiology. The vast majority of stars in our galaxy are red dwarfs. These stars are small and relatively cool, meaning their habitable zones are located incredibly close to the star itself. However, red dwarfs are notoriously violent, unleashing solar flares and stellar winds exponentially more powerful than our own Sun. If an exoplanet is orbiting within the habitable zone of a red dwarf, it is being subjected to a relentless magnetic and thermal assault. For a rocky world to maintain an ocean under those conditions, it would require a planetary magnetic field so powerful it defies our current geological models. If a planet lacks a perfectly calibrated gravity, well, a hyperactive liquid metal core and an atmospheric cold trap, any water delivered during its formation will be violently stripped away in its astronomical infancy. This implies a terrifying reality for the Drake equation. The universe might be highly efficient at creating oceans, but it is brutally efficient at destroying them. The Great Filter might not be the genesis of life, but rather the incredibly rare, perfect physical containment system required to keep a planet wet long enough for that life to build a technological civilization. Up to this point, our physical evidence for the chemical makeup of the early solar system has largely relied on meteorites that survived the fiery, catastrophic plunge through our atmosphere. While these rocks have provided invaluable data, they suffer from a severe forensic limitation. Once a meteorite strikes the ground, whether it lands in the freezing expanse of Antarctica or the scorching sands of the Sahara, it is immediately compromised. Earth is a fundamentally wet, biologically loud environment. A rock sitting on the surface will rapidly absorb terrestrial moisture, weather under the atmosphere, and become colonized by microscopic bacteria almost instantly. To truly read the uncorrupted chemical history of the solar system, we had to eliminate the Earth from the equation entirely. This absolute necessity for pristine, uncontaminated evidence triggered a new era of orbital engineering, culminating in the complex mechanics of the modern sample return mission. To find the truth, we had to intercept the debris of the early solar system directly in the vacuum of deep space. In recent years, the scientific community achieved a monumental milestone. The Japanese Hayabusa 2 and the American OSIRIS-REx spacecraft successfully rendezvoused with two near-Earth carbonaceous asteroids, Ryugu and Bennu. These spacecraft did not just orbit and scan, they physically descended, violently disrupted the asteroid surfaces, captured raw material, and fired those sealed containment capsules back to Earth. These samples were never subjected to the searing heat of atmospheric entry friction, nor did they ever touch the terrestrial biosphere. They were pristine, vacuum-sealed time capsules representing the absolute beginning of planetary accretion. When geochemists finally opened these containment capsules inside highly controlled, hyper-clean isolation chambers, they were expecting to find the standard hydroxyl ions, chemically bound to the silicate minerals, exactly like the carbonaceous meteorites we had previously analyzed. But what they discovered, hidden inside the microscopic architecture of these extraterrestrial rocks, shattered the established boundaries of planetary chemistry. Deep within the crystal lattice of specific minerals, particularly iron sulfides and carbonates, researchers found something entirely unexpected. They did not just find trace molecular hydrogen, they discovered actual physical fluid inclusions. Trapped inside these microscopic mineral vaults were droplets of pure liquid water. This was a profoundly shocking realization. These were physical drops of fluid that had been permanently sealed in the dark for 4.6 billion years, dating back to a time before the Earth had even fully formed its molten core. But the analysis revealed an even more staggering truth. The liquid, trapped inside Ryugu and Bennu, was not pure distilled moisture. It was highly carbonated water, dense with dissolved salts and complex chemical compounds. This leads to a massive paradigm shift regarding the physical nature of asteroids. We inherently view asteroids as dead, static rocks tumbling through the freezing void. But the presence of this carbonated fluid definitively proves that the parent bodies of Ryugu and Bennu experience widespread, dynamic aqueous alteration. Shortly after these asteroids formed in the early solar nebula, the radioactive decay of short-lived isotopes, specifically aluminum-26, generated intense internal heat. This radioactive heating was powerful enough to melt the massive reserves of ice trapped inside the rock. For millions of years, the deep interiors of these dark asteroids functioned as warm subterranean oceans. Liquid water actively flowed, percolated, and reacted with the surrounding silicate rock in the freezing vacuum of deep space. But the water did not flow alone, and the implications do not stop at geology. Coexisting within these pristine fluid inclusions, scientists identified a staggering array of complex organic molecules. Dissolved in this ancient extraterrestrial water were vast quantities of amino acids, the fundamental building blocks of proteins, alongside polycyclic aromatic hydrocarbons and uracil, one of the 4 essential nucleobases that form the structure of RNA. At a planetary scale, the meaning of this discovery changes our entire understanding of the origin of life. We have spent centuries assuming that the complex organic chemistry required for biology was a miraculously rare event, an exclusive spark that could only occur in a warm, shallow pond on a highly stable, habitable planet. But the fluid droplets inside these asteroid samples prove that this assumption is fundamentally backwards. The dark asteroids were not merely dumb transport vehicles carrying dry rock. They were active, deep-space chemical reactors. The liquid water inside them acted as a universal solvent, driving complex prebiotic chemistry and brewing the foundational architecture of biology long before it ever fell from the sky. If the fundamental building blocks of life pre-dissolved in liquid water are already present in the leftover rubble of planetary formation, then the universe is practically aggressively seeded for biology. Every rocky exoplanet coalescing in the habitable zone of its star across the entire galaxy is being bombarded by these exact same organic, water-rich packages. The raw materials are a universal standard, and precisely here, this undeniable proof of cosmic water begins to connect with a much larger, darker question surrounding the Fermi paradox. If the entire architecture of the cosmos naturally mass-produces liquid water and complex organics and automatically delivers them via gravitational dynamics, then the galaxy should logically be teeming with sprawling, technologically advanced civilizations. The fact that our radio telescopes continue to hear nothing but silence implies a terrifying reality. Acquiring oceans and the chemical precursors to biology is actually the easy part of the cosmic equation. The true great filter, the insurmountable barrier that prevents the rise of interstellar life, does not lie in the physics of planetary formation or the delivery of water. The delivery is a cosmic guarantee. The ultimate test of survival lies in what a planet manages to do with that water once it arrives, and whether it can hold on to it long enough for the slow, fragile engine of evolution to take hold. When we zoom out from the microscopic fluid inclusions locked inside ancient asteroids and look at the broader canvas of the Milky Way, our entire perspective on the rarity of Earth completely fractures. For generations, we operated under a deeply ingrained geocentric bias. Because we live on a wet world surrounded by dead, dry rocks in our immediate solar neighborhood, we naturally assumed that oceans were a miraculous cosmic anomaly. We believed that liquid water was the ultimate prize of a planetary lottery, requiring an impossibly lucky sequence of orbital migrations and perfect impacts. But modern astrophysics has systematically dismantled that assumption. The presence of water is not a miracle. It is an automated mathematical algorithm running constantly throughout the universe. To understand this universal inevitability, we must look at the fundamental chemistry of the cosmos. Hydrogen is the absolute baseline material of reality, forged in the immediate cooling aftermath of the Big Bang. It is the most abundant element in existence. Oxygen, while heavier, is the primary byproduct of stellar nucleosynthesis, continuously forged in the crushing cores of mature stars and violently dispersed across galaxies during supernova explosions. Oxygen is the third most abundant element in the universe. When you take the first and the third most common elements and place them in the turbulent energetic environment of a molecular cloud, the laws of thermodynamics dictate an unavoidable reaction. They bond. Consequently, standard water is the second most abundant molecule in the known universe, trailing only molecular hydrogen. When astronomers point radio telescopes at distant stellar nurseries, like the Orion Nebula, they do not just see gas, they detect the chemical signature of water vapor being manufactured on an incomprehensible scale. These vast interstellar clouds are actively generating enough water to fill the oceans of Earth millions of times over every single day. If the raw material is universally abundant, the mechanical delivery systems must also be universal. The advanced models of planetary formation we have explored, from pebble accretion to the direct atmospheric ingathering of nebular gas, do not require any unique Earth-specific magic. They are basic functions of gravity, fluid dynamics, and thermodynamics. Every single star in the galaxy is born from a collapsing disk of gas and dust. Every single one of those disks possesses a thermal gradient and a freezing snowline. Therefore, every single rocky planet coalescing within a habitable zone will be subjected to the exact same inward drift of icy pebbles, or will possess the exact same trace hydrogen baked into its primary mantle rock. The chemical synthesis of an ocean is a default hardware feature of planetary assembly. This leads to a profound shift in observational astronomy. When we utilize next-generation instruments like the James Webb Space Telescope to conduct atmospheric spectroscopy on distant exoplanets, we are no longer surprised to find water. We expect to find it. In analyzing the light spectra of transiting worlds in systems like TRAPPIST-1, we are actively searching for the absorption lines of water vapor, and the data increasingly suggests that the galaxy is overflowing with wet planets. But the abundance of water introduces a severe counterintuitive problem for astrobiology. If the mechanics of planetary formation are so highly efficient at delivering water, they are often too efficient. Earth is actually a remarkably dry planet. By mass, our global ocean accounts for less than 0.1% of the planet. We are a rocky world with a very thin coat of condensation. But when we look at the exoplanetary data, we find a massive population of worlds, often called super-Earths or sub-Neptunes, where water makes up 10, 20, or even 50% of the total planetary mass. These are true water worlds, and at a planetary scale, the meaning of an ocean changes entirely when it becomes that deep. If a planet is covered by an ocean that is hundreds of miles deep, the barometric pressure at the sea floor reaches millions of times our standard atmospheric pressure. Under that kind of crushing geological weight, water breaks the rules of standard physics. It does not remain a liquid. The extreme pressure forces the water molecules into highly dense exotic crystalline structures known as Ice 7 or Ice 10. This deep ice does not require freezing temperatures. It is hot, solid ice forged purely by gravity. This creates an apocalyptic barrier for the genesis of life. The solid layer of high-pressure ice completely seals off the liquid ocean from the rocky planetary mantle below. Without direct physical contact between the liquid water and the silicate rock, there can be no hydrothermal vents, no chemical weathering, and no transfer of vital minerals like phosphorus or iron into the water column. The ocean becomes chemically stagnant and biologically sterile. A planet can be utterly drowning in water and simultaneously be entirely dead. And precisely here, this mechanical reality connects directly to the great silence of the Fermi paradox. For decades, the Drake equation relied on the assumption that finding a planet in the habitable zone with liquid water was the primary bottleneck for the emergence of civilizations. But if water is everywhere, and if planetary formation automatically guarantees its delivery, then the Great Filter must be far more specific. The true cosmic rarity is not water itself. The rarity is the precision of the water budget. A planet must be massive enough to hold onto its atmosphere against the solar wind, but small enough to avoid becoming a gas dwarf. It must accumulate enough water to lubricate plate tectonics and regulate its climate, but it must reject enough water to prevent the formation of a crushing, suffocating layer of exotic ice on its seafloor. It needs exposed continental landmasses to allow for the chemical weathering that drives the carbon cycle. When we look up at the night sky, we are likely looking at billions of oceans. There are worlds entirely encased in ice, and worlds covered in boiling, high-pressure supercritical oceans beneath thick atmospheres of hydrogen, a theoretical class known as Hycean planets. The universe is incredibly skilled at making planets wet, but the deafening silence of the cosmos suggests that keeping a planet perfectly, shallowly wet over billions of years, allowing just enough dry land to breach the waves for technology to eventually ignite, is a tightrope walk of orbital mechanics and geophysics that very few worlds ever survive. For decades, humanity sought a single, elegant answer to the paradox of our oceans. We looked for the lone cosmic smoking gun. But the true story of Earth's water defies simple narratives. It is not a single isolated delivery. It is a 4.5 billion-year-old cocktail blended by planetary violence and cosmic fluid dynamics. Every glass of water you pour is a mosaic of the early solar system. A fraction of those molecules was baked directly into the dry rocks that built our world from the very beginning. Another portion was inhaled directly from the primordial cloud of hydrogen gas that preceded the sun. A significant volume crashed down in the dark. Heavy carbonaceous asteroids hurled inward by Jupiter's chaotic migration, and another layer drifted in as a relentless blizzard of frozen pebbles from the freezing outer dark. All of this material was churned, sealed, and protected by the catastrophic impact of a rogue planet. Earth is a hydrological chimera. The moisture within our biosphere is a composite of the deep interior magma and the absolute furthest fringes of the solar system. This leads to a profound realization. The universe does not make wet planets through luck. It manufactures them through multiple, overlapping, highly efficient automated systems. Water is a fundamental default of planetary assembly, but if the cosmos is flooded with the raw materials for life, why is the galaxy so remarkably quiet? Because, as we have seen, the true Great Filter is not the delivery of water. The Great Filter is the razor-thin margin of planetary survival. It is the requirement of a perfect gravity, a hyperactive magnetic shield, a deep tectonic recycling engine, and an atmospheric cold trap. The universe gives water freely, but it is ruthlessly efficient at taking it back. To test this ultimate limit of habitability, our gaze must now extend far beyond our local stellar neighborhood. We have exhausted the meteorites and asteroids of our own system. The future of planetary science lies in the deep sky. This is the era of advanced atmospheric spectroscopy. Space observatories like the James Webb Space Telescope and the massive ground-based arrays currently under construction are not just looking for rocky exoplanets. We are waiting for distant worlds to pass directly in front of their host stars. As the starlight filters through the alien atmospheres, we catch the shadows of molecules. We are actively hunting for the specific chemical absorption lines of water vapor in the stratospheres of alien worlds. But the next great leap in cosmology will push the boundaries of physics even further. We are developing the technology to measure the precise isotopic ratios of heavy deuterium to standard hydrogen in the atmospheres of planets dozens of light years away. When we achieve this, we will not just know if an alien world is wet. We will be able to read its deepest chemical history. We will know if it inhaled its oceans from a nebula, if it was bombarded by icy pebbles, or if it is currently losing its atmosphere to the stellar winds of a violent red dwarf. We will finally be able to map the true distribution of sustainable oceans across the Milky Way. When you look at the ocean, you are not looking at a local geological feature of a terrestrial rock. You are looking at the oldest surviving artifact in the solar system. The molecules crashing against the shoreline were forged before the sun even ignited. They survived the radiation of the stellar wind, the apocalyptic melting of the mantle, and the endless, crushing cycle of plate tectonics. We are born from a universe that is inherently eager to create oceans, yet incredibly hostile to their long-term survival. Understanding exactly where our water came from is no longer just a forensic history lesson about the Earth. It is the definitive roadmap we must use to find out if we are truly alone in the dark.